15 or 16?
15.
15, yeah, okay. Okay, let me see. Oops. Okay, wait, I should be able to. No. And then let me see. I can put it back. Okay. Okay. Okay, you can see the screen, Christopher?
Yeah.
Okay. Okay, so we have water in the container filled to a depth of 0.5 meter. Okay, the density of water is, okay, 1,000, of course. Calculate the pressure on the base of the container, X. Okay. Explain why the pressure at X must be equal to the pressure at Y. Okay, so, all right, okay. And explain why the force downwards on the base of the container is larger than the weight of the. Okay, all right, okay. So, all right, so, okay, what is it? What is it question A, first of all?
Yeah.
Okay. So, question B and C is basically okay, right?
And not really, because
Okay.
I don't understand the question, because when it says point X, I assume that because the other, like, 2/3 of the parts are 0.3 height,
Mm-hmm.
and only 1/3 of the height of the area of the height is 0.5.
Yes. Um, it's a bit a tricky question. I agree. Um, okay. Of course, it goes back to question number A, right? Same thing. Um, point is, what is pressure?
Uh,
Just in its most basic definition.
force per area.
Yeah, exactly. Huh? Okay, so the point is therefore we will. I mean, we will have, assuming here, the same area, but it's not explicitly said, of course, here, right? We just can assume it. We're talking about the same area, be that in position X or Y, so to speak. And when the force acting, um, of course, is how to say that. Um, okay, let's have the same density. So when what you calculated was 0.3, right? What was the depth you said?
Um,
When we go back to A, so here, sorry. So I mean here, right?
yeah.
And you have G and you have the density, and um, so we know that they are equal, huh, in distance here. That's what you say here. So this is, I guess, what is coming from the lesson with the teacher.
Uh, they gave us the marking scheme.
Okay, okay, okay. So I think so one part is the pressure from the same body of water in the same depth. So because um, what is this one, or what is this part?
The the volume of water.
Yes. And what the red one, what does it explicitly mean, what I just highlighted? When you look at the question, right? So what does that represent? That's why it's a bit a trick question.
So the area in contact with the water.
Okay, but we are not interested in the force to the side one, right? We're just
Yeah.
interested in the one downwards. Wall, right? Of the container. So in other words, this is the container. Now, when you look at, is the container closed here?
No.
Mm,
Oh,
actually, yes, right. It's
yeah,
it's
yeah,
just
yeah,
a
yeah,
container,
yeah,
right? That's what I mean. I know. It's the question is a bit, and we don't know if that one is actually open or closed, right?
yeah.
It doesn't say. Is there a lid on it or not? But the point is really this one. It's filled to a depth of 0.5. So, in other words, the atmospheric pressure is not acting here onto the water and not here and not here and not here, because this is obviously a container on your, for example, on your kitchen table, right? I mean, of course, the dimensions are a bit too big for that, 0.5 meter, but just to say, it's just, or stands on the ground, whatever. So it's like a half a meter, could be a tank, for a water tank for fresh water supply to the house or something like that. So when we talk about pressure in the container, what is the relevant or pressure added to the atmospheric pressure which is existing here, the P, then what is counting? And this is a bit, of course, a tricky example, but just follow the basic lead. If the container would be like that, then, and I tell you this is 0.5 meter, then what would you say is the height I have to include for my pressure calculation?
Just 0.5.
Exactly. So does therefore the 0.3 meter mean anything in terms of pressure?
No.
Exactly. Exactly. This is a bit difficult to fathom. I understand that, but think of it that this is pressure. So this is where the force from the atmospheric, I mean, the air, as we discussed, not last time, but one of them before. This is basically the weight, kind of, and the resulting force of our air, oxygen, nitrogen, and whatever else is there. And that presses here onto this one. And because and so I have, to make it simple, I have my one atmospheric pressure, my 1 atm, right? The 1 kilopascal on this surface. Now you may argue and say, well, hey, there's a container here, so what about that? Yes, but it's not that because it's 0.2 meters and only starts here, it has zero impact on the pressure inside of the water tank. The one thing which is really only counting is this one, where you have the contact with the surrounding. Or in other words, um, you can have a, let's say you would have a water shaft. Now let's do it like this. So it's on the ground, so that's where the surface is, and you have some kind of reservoir underneath, and it's all filled from the top to the bottom, filled with water. Then for the pressure down here, the only thing that really counts is that difference. Let's say that would be maybe 20 meters. That would be a reasonable depth for a freshwater fountain, for example, where there is some kind of reservoir coming in from the surrounding, right? The water goes through the gravel and everything, whatever is here. And for whatever reason, long time ago, maybe somebody made kind of with stones, make kind of a cave down there in order to contain the water. Not that it seeps out down here, but it goes the other way around. It goes into it. That's just details, but just to give a bit an idea. And then the pressure at the bottom here is really only that one. That is the so-called water column. Because pressure is going, how to say, it's like equalizing. You will not have a different pressure here, or a different pressure here, or a different pressure here. I mean, yeah, of course, slightly, because it's not as deep as the 20 meters. But what all that counts in the end, or let's make a cut and do it like this and say, okay, that's where I look at it now before I look at the bottom. Then everywhere here, I have exactly the same pressure. Oops, make it orange. I have the same pressure because it distributes itself. You can see that, just imagine, it's a bit difficult to explain in the last detail, but imagine when you have water or oil, maybe better because water instantly dissipates. Oil is a bit more sticky, has some surface pressure. It will kind of evenly distribute itself, right? If you have some oil on the surface and it's kind of a it just stays there, it will start to spread out evenly in tendency. So because of the pressure distribution, pressure always means it goes even. It's like in a tire where you have it here, then you will have everywhere the same pressure in the tire from what is inside the tire in terms of air volume, in order to make the pressure, obviously an overpressure to inflate the tire, the tube. So everywhere is the same pressure. So that's, of course, goes back to question number B, is that you cannot have a different pressure at a different point, because it doesn't matter, or what matters, let's phrase it positively, what matters is that difference in height which applies the pressure. And then you can imagine that basically it's like a flow of forces which then will evenly distribute. So this one, which we call pressure, is actually a certain force per whatever square meter, right? And then it will distribute itself based upon the additional weight of the water. And the additional weight of the water is everything which is in here. It's just that the further down you go, the more it counts, because that is basically from the acceleration. That's where it comes into play. So the water is like one, I mean, you can, when you think back and say, okay, I have the density of the water and I have the volume. So density times volume gives me the mass, right? Agree to that, Chris?
Yeah.
Density times volume. Huh? So that means the mass. So when you think of back to potential energy, for example, that's a good example always. Then you can clearly say, well, if I'm here, I have a different potential energy compared to there because of the height. It's a bit similar to what we experience here, because we have this force field. Oh, that should have been red, sorry. The force field, which the moment you combine mass into the force field, you have a force, right? Or the gravitational field creates the gravitational field force the moment you have the mass in the field, so to speak. And that's why we have a different situation, or energy-wise now as well. Excuse me. So, okay, we are back, but now, of course, shifted slightly. Okay, more or less. So, because the higher the gravitational field, and that's the key actually here to the answer, is at the center of the Earth. this is, or in any, at the center of a body, that's where the highest field force will exist. The further away you are, the less the field force will be compared to a mass. That's why high on the mountain and at the bottom of the mountain, there's a different potential energy. So I have to do work because the field force is going to the center. That's very important. It's a directional, it's a force, it's a vector. So I have to apply work to move it up the mountain. I go against the field, or I go with the field, but the field does the work for me, so to speak. So I don't have to provide work. It will be provided onto the body because it's there, so to speak, kind of like magic, but of course it's not. So it will be so because the mass will be drawn by that gravitational field, and that is the force going in that direction. So the further down you go, the more work it will be, or the other way around. And that's exactly what we have here with that water column. This is the one which then defines, because all the water drop, but imagine that they will be distributed according to that force field. And at the end, what counts is, and we are talking about x, huh? We are not talking about, x and y. We are not talking about here. We are not talking about here. We are not talking about here. We're talking about this one, purple. And that is the one we are taking into account. It would be different if I would be here, it would be this one. And of course, for this one, it's this one, etc. Because of the gravitational field force. So the key here is actually, I have to realize, of course, at that moment, of course, it's a combination of volume and the field force and the height, as it says in the formula, actually. So if I'm here, then of course I only have that volume which counts, and I only have that height. Of course, I still have the same field, that G, right? That's the normal. But obviously, under the influence of that lesser height and that lesser volume, of course, I have a lower force, and in consequence, because of the diameter here, the area, I have a lower pressure. I will have a higher pressure here because it's still the same area, it's still the same density, but the volume has increased simply because I have, for example, doubled the height from before, right? I take double. So, of course, height times radius, if it's roundish, then, of course, I have a different volume. So the mass is more. And the mass in combination with the acceleration will create a different force. And henceforth, the pressure here will be double if that compared to here, because the force has doubled, because of the height has doubled, and the volume has doubled, but the diameter, the area is still the same. Hence, the pressure has just doubled as well. Is that okay so far?
Yeah.
And if you go further down, then of course your area will suddenly change, so it will go different. So luckily the question is, because that would be a complicated question to say, what is the pressure here and what is the pressure there? So I'm erasing whatever I did here, because we need to have a bit of clarity here. Then you would have to have some more information and say, okay, actually we have the information. Then we can say this is of course 0.2. Oops, 0.2. But of course, and I know this one, there's like you right, there's 1/3, right? So this one is only 1/3. What we don't know if that's a cylindric. So a cylinder, if I look at it from top, is it something like that? Or is it a square, right? Is it just something like that? And I have the opening like that. Or I could still have the opening like roundish. That would all have an impact on my area, right? But
Yeah.
we are not going that far. It's just to illustrate a bit the challenge. So this problem here is already a bit simplified because we are only talking about X and Y. If we will talk about X and Z, for example, then it will become much more complicated. Or, in other words, I would need more information about the geometry of the whole construction, so to speak.
Wait, why?
Because when you are here, that's a good question, because here you would have a different area. Let's say it's squarish, huh? Makes it a bit easier for the time being. So if
The
that would be a square here, then of course all the pressure would be on that square if I'm at that height. So that means as its volume, of course, is the water. That's just the 0.2 times whatever depth it has. And we don't, and of course, to really calculate it, I would need to know what this is. If I assume this is 0.5 and that could be 0.6, just to say, right? Then of course I could say, well, obviously, then it's this area in order to calculate the pressure. But from the first, I come from the force, and the force is related to my volume, which is resulting with the density into a mass. Then I have G, so I have a force. And then I have to apply the height the height is already applied because this is part of the mass, right? In other words, the force is higher simply because there's more water. That's it. So and that don't let how to say don't let the drawing is a bit misleading because it basically implies that the water is only 0.3 here, but that's not the point. The point is when we talk about the volume and not just the height, that is making all the difference. Until now, we have okay, I go back to that. I erased that. Until when we talk about the formula for the calculation, right? Then we say also delta P. I just write it down once more. Delta P is nothing else but our force over area. Okay, area. Huh? But as we talk about a three-dimensional object, we talk about density times area times height. So here, this is my volume. And here is my mass. So that is all related to the force. So this is this one. And I need my G. So this red part, oops, that should have been red, sorry. This is my force because it's mass times G, just very classic Newton, right? That it says force is mass times acceleration. So, and this is nothing else but the mass. So what count? The H is a bit misleading. It's not really the height of the water column which counts, but it's part of the volume to calculate what is actually in there. So partially you were on track, but in order to get the volume, you would need, of course, the final dimension of the container. Because, in other words, Chris, what did you calculate here?
I assume that the top part stretched all the way from like the length that we don't see is the same.
Right, exactly, right. So, I mean, we don't know the depth either, right? Actually, right, when you think of it. So that's why basically we are missing the depth and the width. So I mean, if that's the width and the depth is of course going into the picture, so like that. So we don't know these dimensions. So all we know is the height. In order to calculate the volume, we need to calculate the. I mean, in other words, in order to calculate the pressure at the bottom, we need to know the volume. But like we do it when we talk about the pressure at the bottom of the sea, we don't know the depth and the width of the sea. So we limit it. We just go in a simplified calculation and go with the H, right? Because that's what we can lead it back to. That's why I want to come back with this one. So this is the force, But you can actually simplify it. Why? That's why then suddenly everybody gets a bit confused because it's all about the height, but we have to put it into perspective. So this is one thing, right? So, and this one has to be divided by the area, huh? Because the red one is the force. Agree with me?
Yeah.
Hmm? So mass times acceleration. On the other hand, we can. So what we do now is a bit different. We say, well, the mass of the water. That's already what I wrote down. Mass is this one times A times H, right? That's what we said. And on the other hand, I can say, so henceforth, the weight force is, of course, mass times G. So, of course, A times H times G. Okay, so that's the weight of the water, right? Like what we just said. This one is a force, right? The force is the weight of the water, which comes from the volume times the density, makes us the mass, times the acceleration. So this is now the weight force. Okay? But now I can say, on the other hand, as force, the delta P is my force over area. Now I can simplify it, because what I can say now is I have my, of course, times H, and I can say G divided by A again, right? Correct?
Uh, yeah.
Because this is the force, right? Because this is the mass.
Yeah.
And this is the weight force, huh? This one. And of course, I divide it by the area because I'm talking about pressure. So, of course, I can make it violet, purple. So, of course, I can eliminate that. So that's why the beauty of the whole consideration is, in the end, I don't need to know the area. So I can limit it and say, well, it's this one.
Oh.
Simply because of my, so that means when I look at my container, I don't need to know this one and that one. I mean, looking from above, huh? Because I can eliminate it, because I'm talking about, that's the beauty of talking about pressure. So it's basically a mathematical proof to show that in order to calculate the pressure change, I don't need to know the area, also obviously this one, because force is related to the area, but pressure is of course divided by area, so the force divided by area here. So I can eliminate the area again, so which leads me back to only density times height times G. Mm.
Yeah.
Mm. Okay. And do you have the right? And what is the um, so when you said, aha, I see. Okay, I mean I mean you were on the right track, if you want to say so. But what is wrong here, Chris?
Uh, because only the height matters.
That's correct, but you made the right conclusion. But some things, what do you have the right answer, by the way, for this one? I mean, not numeric.
Uh, wait, let me.
Just to cross check, then. I mean, that would be good to have that as the final answer.
4905.
Okay, right. So when you think of this, so I mean, this is a good approach, and say, well, I'm talking about one third, one third, one third, right?
Yeah.
So you are on the right track, but the ratios don't match. That's you did the right thinking, but the wrong ratio. So you come with the density, of course. So you already take it out of the equation. The G, the density, that's the same, because what you realize, rightfully so, is to say yes, the height counts of the water column. This is a special case, but I don't need to know the area, right? But I need to know the ratio of the different heights, because not everything is H here. I mean, H1. I mean, I tell that H1. Sorry. So when you look at 0. If you look at this one, and this one, so you say this is 3/3, right? 1, 2, 3/3, right?
Yeah.
So what is the ratio of the one which is 0.3 meter high out of these three?
2.
Okay. And what is the one with the height of 0.5?
Just
Of
1.
the also one of the trees, right?
Yeah.
So how about if you say I have 2/3 at H1 and I have 1/3 at H2, and of course I have the density and the G. Whereas we say H1 would be 2/3 times 0.3. Oops, sorry. As 1/3 times 0.5.
Yeah.
So that would be 0.2 plus or 0.5 1/3. Of course, 0.166. So 0.366 times. So what do you get for what 2/3 0.3, 0.5, yeah. But let me see, 0.3 times 2 divided by 3, and 0.5 divided by 3 plus 0.2 times 9.81. Why did you get 35.97, Chris?
Hmm? Um,
So because you get 0.2 divided by 3, right? Plus 0.3. So that
um,
so if I execute your calculation, then you have 0.2, right? 0.2 divided by 3 plus 0.3. So how did you come up with that one times 9.81 times 1,000? I mean, I see why you have the number divided by 10. And the result you said is 4 point how much? 49. Okay. Yeah, what is the model? I mean, the reference answer, the 4,900. You said, I think I heard for the correct answer here.
yeah. 4,900
Just 4,900
and 5.
as 05. Okay. Oops, 05 Pascal. Okay. So, hmm, so 4,000, 4,905 divided by 1.81 divided by. Yeah, I know what they do, but I don't agree really. You know why the answer is 4,905?
Because they directly just use the height as 0.5.
Exactly. And I mean, in my opinion, it's not correct. You are correct. It's just a bit the way you calculate it is a bit to me, uh, you know, to me it's like what we said or what I tried to explain. Let's put it like that. The key driver is the pressure difference is a result. I mean, I just a force over area, hmm? And force is the weight force. That's what it is. That's why the deeper you go, the more weight you have. I mean, the more mass you have because simply the height is changing, assuming the same area because we can divide it by area, right? So this is the point here that we have the situation that the mass is density times area times height, which is the mass times g. That's the force, and I can divide that, and because the pressure so is the same. So that's why the goes back to the point as well that across the floor of that one must be the same pressure. It cannot be a different pressure from one point to the other because it's the mass of the water which is the same. You know what I mean, Chris? Right here at the bottom of the container, it's the same mass. You have the complete mass of the water here. It doesn't matter if you're here or if you're here because it's everywhere the same mass, resulting in the same weight force. And then from X to Y, of course, it's the same area. I mean, we're in the same spot here. So, of course, as the mass is the same, so that means the force is the same because it's the total volume which was making it happen. But the volume is defined by the zero point 0.3 here, the zero point 0.3 here, times whatever area we have here, times the one we have here. And then, of course, times the height. So this one contributes with this water column, and this one contributes with this water column, and this one with this one. But it's just the mass in the end which counts, which is adding it all up. So in the end, you have the same force here, the same weight. So if you take a body, then of course you have the same weight force here because of the volume you created, meaning the mass you have. What would be different is if there would be a separator and you would have oil on this side and you would have water on this side. Then of course it's something else, right? Because it has different density. But the moment you doesn't matter even if you mix oil and water and disregard that oil is a bit of course floating. You could make it complicated and say then oil is floating on the surface, it's not down here. Well, it doesn't matter because it's still adding to the total mass of the whole container, right?
Yeah. But,
If it's then floating on top or floating at the bottom, it's not really relevant for that. Yeah.
but because my teacher in the marking scheme says that
Mm-hmm.
it's the height is 0.5,
Mm-hmm.
regardless if like the container, like the two corners, has missing volume. So then they say that the force due to the pressure is greater than the force due to the weight, because the pressure is the 0.5 height times the density and g, while uh, the weight is the volume
Mm.
times the uh, density and the volume.
Yeah, this, so why okay, but that's for C. Why the force downwards on the base of the container. But that's a different. You talk about C now, Chris,
Yeah,
right? That's a different story, right? Okay, I mean I know. I mean I do not agree with that result. Sorry, because you're on the right track. It's just that you have put the numbers a bit wrong. It gives the same result, but what I'm saying is that okay, let's do that like this. So for A, we have the. I mean, I just write down what you already know, but nevertheless, sorry, why is that flipping around? So pressure is force over area. Force. It's a bit flipping. Sorry. Force over area. Now the force, so we still have the area. The force is um, mass times oops, that's an ugly n, is mass times acceleration, huh? Just Newton. So what counts to me is henceforth, regardless, whatever I have in a container, or in such a container, or in such a container, or I could even have an extension here, I mean closed of course, and here, then the whole volume here is creating the force. So what counts, but we can simplify that, but it's how to say, um, this becomes very complicated because it's not so easy as what we just calculated now, right, with this one. So if that is true, what it says, then all that counts. So what I want to tell you is the following. I do it once more. If I have three different bodies, one is a container like this, one is a container like this, and one is, for example, a cylinder like that. So this one has this height, this one has this height, which is different. And okay, I make this a bit better. And this one has that height, right? So as according to what we say, oops, times h times g, then and it's all with water field, then this one would have the highest force. Oh, this one, right? Because it has in my drawing. I mean, maybe I don't do it three-dimensional. I just do it, but it would be a cylinder, just to say. So it would have it would be higher like this. Would you agree that this one has the highest pressure?
yeah.
Why?
Because it is a highest the height.
But when you look back at the force, I know what you mean. Then it's mass times A. So A is constant, right? So we have the G force. So there's no difference. So in all three, I have G force. And the only thing which counts is the mass, according to this one, right?
Yeah.
And the ratio of the mass to the area. Or maybe let's make it like this. Maybe better even. Then it becomes even more clear to what I want to say. So if you now have, sorry, if you have this one, right? So this one has the highest height. But does it necessarily have the highest volume, the highest mass? Not necessarily, right?
Mm.
Maybe yes. I mean, now in this drawing it says the highest volume, so
Yeah.
it will have the higher mass. But assuming um, the this one, but because the area, let's say, let's make that in orange. So that area is the same for all, because that's what counts is the area for all. And I have then, and but if I look at it from the top, I could as well have, now I'm looking from the top, this one could be like this one could be like this, and this one could be like this. So do they have the same area? No. Right? When you look at, you know what I mean, Chris? This is from the top, right? I look at it from the top. So this is from the side, and then I look at it from the top. So this one is very large in area. This is comparatively small, and this is even smaller.
Oh.
So of course the area has to be identical, otherwise I cannot compare it, right? So it's not just the height which counts. That's what I want to drive at. It's really the area. So when I divide the mass divided by the area, then I have to talk about the same area involved in both the mass and the area itself. Or in other words, that A here, my density times area times height, has to be the same A as what I'm dividing it. Otherwise, it doesn't work.
But if the density is the same, then we can compare it because
As long as the A are the same,
no, but because
right?
because
It has to.
when area increased and force increased, then the pressure is still the same.
Yes, yeah, of course. Yeah, absolutely. I know. Yeah, you're right. But if you compare three different bodies, right, you have to say this is the same area for all of them.
Huh.
Hmm? So, in other words, so when you look at, I mean, when we look at our example with this one, then of course here must be that must be the same area as this one, as this one. But we came from the force, and the force as a result of the mass and the acceleration, hence the mass as a result of the volume times the density. And the volume is, of course, the dimensioning, also height times area. So the height is varying from here to here, but it has so the height times area is divided by the same area, right? So that one is the same as this one, as this one, as this one. But so in other words, when you look at it, I know it's a bit. So when you look at this one from the top, then they have the same area. They're like that. So like this, huh? 1/3 each, like what we said here. 1/3, 1/3, 1/3. So each one is 1/3, right? And they have the same depth. So we're talking about the same identical area. So the area is the same, but so volume times height is mass, also times density, of course. But the volume for the second one here is different because it's higher up. And the volume here is less because it's only 0.3 meter high, and this one as well. So what counts for the total pressure is in the end how much volume you have in the container, nothing else. Whatever the shape of the container is doesn't matter. What matters is how much water do you have in the container at the end of the day, which is the mass times the acceleration creates the force, and then of course it's the force on the whole area. Do you follow me, Chris?
I'm thinking that because density and area doesn't change, then shouldn't the density doesn't change, then shouldn't the force and area be proportional? And then we only have to focus on the height difference.
But you have to calculate the pressure at X on the base of the container. Oh, okay. I see now what is going on. Okay. You know what, Chris? They make a simplification which is okay for the level. Okay, sorry, that's my bad. In that sense, they ask for the pressure at X, but they say the pressure at X must be equal to the pressure as Y, right?
Yeah.
And are from the same body of water in the same depth. Well, the depth doesn't really matter because I like your answer. Because the pressure of X is because it's from the same body of water. It doesn't change. Maybe you should say mass instead of body of water. But other than that, the depth has nothing to do with it. I mean, just because we are here at 0.3 meters and here we are 0.5, that's totally irrelevant. What is relevant is that what I try to explain is all the time is that it's the mass, like what you call the body of the water, which counts. Because the mass times the acceleration, the g-force creates the force. So if what would be the right when I'm at that height, of course I have less volume, which is relevant for the pressure at that height, or the force, so to speak, because that part of the water is not existing in terms of weight pressing down. You know what I mean?
Right.
So when you are looking at sorry, when you look at the let's make a very simple container like that, and it's filled completely with water. So this is the height of the container, but I split it into H1 and H2, huh? And that is just H total. So if I'm at this height of the at that depth, let's call it depth. If I'm at that depth, then what height is relevant to calculate my pressure? I'm here, huh? So what is relevant for the pressure at any of these points? Chris?
So
It's very straight. I mean, nothing tricky. Just what you already know. Just to make it as a very hopefully a very clean example to that we come to an understanding what it's all about. So at that height or at that depth, it's all full of water, huh? Same density.
yeah.
And I'm at that height, so it doesn't matter where I am. So what is defining the pressure on that height or at that depth of the pool. Let's call that is like a tank or pool. Which of the heights is relevant at that point?
Just only the height up to that point.
Exactly. And why is that? Because only the mass of the water up to that point is relevant, or the volume of the water going one step behind. Huh? So what counts here is actually the force times acceleration. Excuse me. It's always the same. So my pressure here, or my delta P1, and here is delta P2, is of course nothing else but force times up. Why do I say always the same? Excuse me. Force over area, because this is the simplified formula. But what we really talk about is actually the volume of the water times the density times the G, right? This is my force. Let's go one step back. Say force is nothing else but mass times acceleration over area, because we talk pressure, and the mass is nothing else but my density times the area times my height. Huh? This is my mass, correct?
Yeah.
Exactly. Huh? So it's the mass that defines it. So the reason why I have at this very point the weight force 1 is because I have the mass of the whole water up to that point. And it's three-dimensional because we talk about volume, right? Sorry, this one. A times H is volume, right? So this is my volume. So what counts is the volume. So of course, if I'm going into the same container further down, it still has the same area in that one, because yes, the height has changed, the area is still the same. So if I calculate pressure point 2 at the bottom of it, is still, this is force 1, this is force 2 over the area. This is of course the second mass times G times A, and the second mass is still the same density, still the same A, but of course the bigger height times A. But the H is a bit misleading, because what we really are interested in ultimately is nothing else but the force. So we have to think of how do I calculate the force at that depth and that depth. And because it's liquid, it could be of course rock, but that's not interesting at that moment. I'm talking about the mass of that body here. And if I would have now a body which has additionally that part on it, then of course that would add to the mass, right? So, but then you could not say, is that height now which counts for the pressure at this level? Because it's only a fraction additional which comes here. It's only a fraction of that additional height comes into play, not because of the height and whatever, simply because it's only a fraction of the additional mass compared to what I already have, which is adding to the force, which is mass times G. So I have additional mass here. And I can see the area, of course, is not the same area. It's just a part of the total area. So hence, of course, the volume I have here is only a part. I mean, now maybe this is now maybe one fourth, a quarter of the area. So, and the additional height then defines, of course, if I assume the same height here and here, then it's just that height times that area times the density. This is my additional volume and hence my additional mass, which is then giving additional weight force to regardless if I'm at that depth or at that depth. But it's then not that additional height which is multiplied with everything else, because I only have that additional mass here. Or in other words, when I make it three-dimensional at height 1, I hope I can do it. So I have this one. Then at height 2, I have additionally, of course, this one. So I have twice the same amount of water, right? So this one is the same as this one. So I have these two boxes full of water. And then I add another box on top, but this is a much smaller box, like this. So this is only a fraction of the total boxes here, but it has an additional height. So does that height now contribute fully to the additional pressure? Of course not, because it's only one fraction of the total volume I have here, meaning it creates an additional weight force related to the volume I have here. And the volume I have is a mix between the area of that smaller box times the height of that box. The height of that box could even be the whole HT, so like this. But the area, as long as the area is only a fraction, of course, it only gives me a fraction of the mass, hence only a fraction of the force, and hence that additional height I'm having here is not suddenly doubling the force I have in the water or the pressure at the bottom here or in the middle here. And if I would be here, you would be very clear and say, hey, wait a minute, the pressure I have at here, at this one, it may be still H1, additional H1, same as that H1, but the area is much smaller, so area of that orange thing, so let's call that area 3, is maybe only 1/4 of area A. So even if I now calculate for that orange box my weight force, then the mass is the same density. The height, yes, is H1 as well, but the area is only 1/4 of the area. I mean, assuming it's 1/4, right? You know what I mean here. This, like I say, this is 1/4 of this one. So that means, of course, the volume of that box is much smaller than the volume of this box, even if the height is the same, because, well, and the depth is the same, but it's a different area because it's only a certain width of that width. And hence, of course, I only have a very different mass box at my disposition, which is a different weight force, which henceforth is resulting in a different pressure addition. Do you follow me, Chris?
Yeah, but my teacher said that it doesn't matter if the
That's
extra
wrong. I
the
know, I mean, I shouldn't say that. But you have to, I mean, the reason why he says that is because you guys calculated with a simplified approach. You only look at the height,
oh
right? But if you look at it, but the question is then, why is then the pressure at X is be equal to the pressure as Y?
because they're the same in the same fluid.
Yeah, that's a good answer. So they're in the same, I like your answer. They're in the same body of water. Because the volume is exactly the sum of everything. So it adds that one and that one. That, of course, is the total body of water, like you say. So that results in a total weight force, which has nothing to do with the height per se. The height is only an expression of to calculate the volume and hence the mass and hence the weight force of the specific bodies.
But if we look at the question C, they
Mm-hmm.
explicitly said that the weight force is smaller than
Of
the
course, of course. Why is that?
uh, it says that because the force exerted by the because you calculate the force by timesing the pressure with the base, but we include the pressure of the height of the entire uh, the tallest height.
Yeah, I know what you mean. Yeah, no, the force why is the force on the base of the container larger than the weight of the liquid in the container? It's a very specific question. I mean, the answer is here, but I can the explanation is very simple because we have already a force here as well. That's why. And that force is the atmospheric pressure. So that's why when we dive, I mean, we know every 10 meters the atmospheric pressure goes up by one atmosphere, right? 1 kilopascal. So this is because we have, of course, already a pressure on the surface, but that's why the pressure on the mountaintop is different than the pressure on sea level, because there's less volume on one side in the air when I'm at the sea level compared to at the mountain level. The density of the air is different. So whenever we have done the mechanical calculation, let's do it here, right? This one, and we calculate the weight force. So here, and we have the box, then we have the weight. So what do you calculate in that moment in mechanics?
Mass times G.
Yeah, exactly, right? Mass times G, right? So you are not including the atmospheric pressure here.
Oh.
Exactly.
But in
But what we do now, yeah?
then the calculations, they didn't, like, there's no mention of the atmospheric pressure at all, because it only calculated the because the pressure is the simplified version,
Yes.
and then we
Yeah?
directly times the area of the base, and
Yep.
that's why we result with higher force.
Yes. Right? It's a bit like when we talk about friction. For example, an object is falling here, object is falling, then usually we are not calculating the air resistance, right? When we do our calculation on that height with that mass, how long does it take until and under G force, also G, how long does it take for the object to reach when it's dropped here from zero and just dropped, hold it out, let it drop. Typical situation in kinetics, right? Or kinematics. Then how long does it take until it reaches? Or we go the other way around and say it takes 0.2 seconds. How height, from which height was the object released, right? That's always without air resistance, right? Because we can't calculate that. It's too complicated. So that air resistance we neglect. Same here. We do not include the atmospheric pressure, that delta P, so to speak, of the atmosphere, which is actually pressing on the body, which is adding weight, but we don't do that. Or we already included in the mass indirectly, but explicitly it's not included here. But now we always have something like this. I mean, the easiest way is to say when you go to the bottom of the sea, right, so to speak. Then of course we have our delta P delta P in terms of the pressure on the surface, plus the delta P, which is nothing else proportional to the mass and of course the type of material, but it's nothing else but the mass of the body, or in other words, actually proportional to the weight force. And like we can show that under the assumption that we have the same area, we can neglect the area, we can take it out of the equation. But that means we have the same area. Then you can simplify it to this one and say, okay, it's just the density of the material times the height times the G, which is fine, which is good enough. But if we go into such a body here, then we cannot just basically say it's the height. What we have to do is to calculate the mass of the total body, like you say, and that mass is the weight force in sum, also the mass of that times the G, because the G is everywhere the same. I mean, 9.81, that's what we calculate. The tiny variations we do not include. And then it's the weight force, and of course divided by the area. But we don't know the area, right? So we typically say then H times, we say then typically this one, but this is under the assumption that it's always at the equal area. So, but if you have a body like this, okay, that's now not the best example because we have equal distances. So that this is basically the body we have to calculate, right? Then yes, we have the same area here, same area here, same area here. We assume it's the same depth, but the height is different. But if we would have now a wall here, then I would agree, is that height. But without the wall, then of course everything counts from the water. Because the reason why we can simplify the calculation is because, well, actually we all come from the force in ratio to the area. That's why we call it pressure. But the weight force is the same, right? Regardless where I am here. So I can be directly here, or I can be, also, meaning underneath that additional weight on the surface, or the additional body which contains additional water, which is filled with water as well. Then, of course, if I stand here, I don't have the higher pressure here compared to here, even if I'm standing directly under this one. But then what about if I stand here? That has a different height. So according to that logic, then that height would create the pressure here, and that height creates the pressure here. But we know, no, that's not true. The pressure here in X and in Y is the same. Like it says it in the answer, right? It's the same.
Yeah.
And the depth you measure from here, it's not because of this one. So the depth X has actually a depth of 0.5 in that logic, and this one has a depth of 0.3. Mm. The only reason I can tell you, Chris, is to say that they would assume that water and air has the same weight or the same density. So that additional body of air is the same as that additional body of water here.
Oh.
Then I can agree, right? But that would have to be stated and say, okay, I understand this is 0.2 meter more. So in the end, this is more air. So contrary to our mechanics situation where we neglect that one, because we say, well, I don't care, it's no additional pressure, we don't calculate it, we simply focus on the mass. Then I could, of course, say here, well, okay, I have additional mass of air, which is creating, of course, additional force. Yes, I agree. But it would then have to be the same density as the water. And then, of course, then I can just say, well, this is imaginary. It's actually a body like that. So my body is actually like this because this part here having the same density as the rest here. And then, of course, everywhere is 0.5 meter. Then I can apply that, what we just said. But this is a dangerous assumption because the air is actually not the same density as water. So hence it's not really true. So that's why the real reasoning is to say I'm coming from the mass, which is the result of the volume, and henceforth, but I can assume I have the same area and the same depth. So hence I can calculate it with what you did here with the third and say, well, it's for 0.3 meters times 2 is the that weight of the that mass applicable, and for this one is this height, and at the same one third of that. Like you said, it's just this one should be 2 times 0.3, or and this one is just 1, so factor 1 to 3, right? It depends on how you calculate it. So you can either say 2/3 of this one and 1/3 of that one, so 0.5. Not the difference here. This is a bit odd. So long story, very long story, sorry about that, is to say the only reason I could list is to say, well, I have the same density for air as for water, hence, yes, then of course it counts at the 0.5 because here is additional volume as well, additional mass, and that contributes, of course, to this one here because it's not in a vacuum. And in order to say I can just simplify and multiply that with 0.5, is that the density in this part would be the same density as in this part. So I have the same mass here as for this one. So it doesn't really matter, frankly speaking. That's the bottom line, right? It doesn't matter if it's water here and here it's air, because if I say the 0.5 counts, then I say the density in these two is the same, because I have the same mass, hence the same weight force, hence, of course, I have the same pressure in the end. Is that okay for you?
Yeah.
Huh? So is a how to say I understand why you are puzzled. I mean, from what, and I actually, again, to repeat that, I like your solution. Huh? I think this is more to the reality, meaning I would just have said make this one 2/3 times 0.3 plus 1/3 times 0.5, because that's what you say, right? But I do. You just come from a different angle. I know what you do. You just take 0.3 and then you take the difference here and say it 1/3. So this is where. So this is the more. This is how it really is, to my opinion. So I agree with you. To say it's 0.5, I have to say only when you calculate the additional mass from these two parts as well, and that air has the same density as water. Yep. Then it's 0.5 all across. Otherwise, it's not. Then it's more. It's this one. But I know the teacher didn't want to go so far, so that's why he just says it's 0.5. So to me, it's a bit a dangerous simplification. Huh? But you don't have to tell the teacher, by the way. But just between you and me, I think it's a bit. Which then a student like you, who really thinks a bit deeper than others, is then going to be confused and say, "Why is it like that? I don't really see it," and I have to agree. I don't really see it either. Your argumentation is more comprehensive. So, and the other one is a bit an oversimplification, huh?
I because when the teacher explained it, he told us that I draw it out. So on the left one, he said that there's a tube of water, and then the bottom block is a wood, and because the pressure of the water in the tube, it broke the wood, and then uh because I I'm thinking, is it because of the height of the water, or is it because of the weight of the water? So then I draw on the right because
Mm-hmm.
I assume that it has the same volume of water, except that
Yeah,
it has a lower height but it's same volume. Then would it
yeah.
also cause the same amount of like damage to the wood?
Mm-hmm, mm-hmm. So that is the question from you to me now.
Yeah, I send like an image.
Okay. Ah, okay. Sorry. I have to go back. Yeah, but I understand what you say. Yeah. Um, okay. So, okay, just explain. I mean, I think I understood what you said. Now, please explain the picture once more to me. Sorry.
Uh,
So, okay. So, what you say, Chris, is that basically the two bodies have the same volume, right?
yeah.
Exactly. So that's what. Yeah. Okay. I agree with you. The height is then irrespective. It's the volume, which is the mass. Yep.
Oh,
Yep. That's why I yeah, we're moving in that direction. So the point is, it can become really complicated. The bottom line is the change, the pressure change, or actually the change of force, right? Ultimately, is but is related to a different volume. The deeper I go, the more volume I have. This is the most simple assumption, right? Assuming everything else is the same. It's the same liquid, it's the same ocean, right? So it's the same width and length. So because it's all across, so I'm diving in the same ocean, so to speak. Even if and henceforth I'm dealing with the same volume. So the deeper I go, of course, the more volume is on top of me. It's very simple. It's like if you water is always we are so used that it's so liquid. It's a bit difficult to imagine with the weight somehow. But if you think, well, uh, 1,000 is actually quite dense, so it would be about the same as like a bag of sugar, right? 1 kilogram of sugar is about the same volume, roughly, as 1 kilogram of water,
Oh,
which is 1 liter, right? So if you think that you suddenly you lie on the ground, on the flat on the ground, and somebody starts to pile 50 kilogram bags of sugar on top of you, you can imagine if you have, let's say, 3 layers of sugar on top of you, that's guaranteed much more weight force on you compared to 1 layer of sugar. That's the equivalent of water depth, so to speak, right? So each layer of sugar bags, as a huge 50 kilograms bag, and you start to pile them on top of each other, one bag on top of the other. If you have 5 bags on top of each other, of course, you have 5 times 50 kilograms on top of you. That is what counts. That mass is what counts. That mass makes the pressure on you because you're still the same Chris, unfortunately, on the 50 kilogram bags of sugar. So, of course, you start to feel a very different pressure on your body compared if you only have 150 kilogram bag of sugar on top of you. And assuming that each bag of sugar put on top of each other is the equivalent of 10 meters of water, just to say. So that means every time you have an additional bag of sugar on top of you, the atmospheric pressure goes up by another kilopascal. So doubles, triples, quadruples, and so on. And that is very clear then, oh, okay, of course, it's the number of bags on top of me, which is the depth. So if you now start to normalize and say, you know what, I don't care about bags of sugar, I just count the height, of course, then I can say, well, you know what, the height of 5 is what makes the change. But only as long as I'm talking about the bags of sugar, right? So to speak.
yeah.
And the moment I'm starting to change it a bit and say, well, okay, I'm having these 5 bags of sugar, but I'm instead of, how to say, um, you are Chris, you have an area, right? So if you, of course, you have to pile them on top of you. But if you now, how to say that? If you now, like what in your drawing, basically, you start to distribute a bit differently, but it's in still the same 5 bags of sugar, so to speak, 550 kilogram bags, but you make it into, let's say that's 250 kilograms, so you make it into 10, 25 kilogram bags, and you start to pile them a bit different. The pressure on your body is the same in average.
Hmm.
Right? The punctual pressure may be a bit different, but the same pressure is applying. So as long as we talk about, um, um, okay, I think what the teacher tried to tell you is to say, well, it's the pressure with the same area. So if you pile up more water on top of you with the same area as the rest, it's the higher volume, hence the higher mass, hence you have the higher pressure. But in water is a liquid, it's not sugar. So it distributes all over. So that's why at X and Y you have the same pressure,
Oh,
right?
yeah.
So it's not punctual. So the body mass force is not a punctual force, it's distributed all over. So that's why the example is a bit tricky, really, frankly speaking. Because of that water effect and the even distribution. So yeah, so I agree with you. Let's put it like that. So what you have here is it's like that weight is really driving it. I mean, the weight force is driving it, huh? I mean, I can tell you this one, Chris. Let me see. So Remember when we talked about the tractor? Because that whole density stuff is not so easy, the whole pressure. If you think of a big fat tires, so this is a truck tire like this, and you have a small car tire. It doesn't really matter, but let's say the same. Looks from the side, same diameter. But if you look at it from this one is a really fat one, so really like that, more like a drum, and this one is a really slim one, right? But both carry the same weight because, simply speaking, they both carry the weight of one quarter of the truck, right? Because each wheel has to, assuming it's four wheels from the top, four wheels like that. So each one has one quarter. So if I now have a fat tire like this compared to this small tire, I mean, same diameter, but not as fat, not so deep as the other. So of course I have a higher area here, right, compared to here. So that means but the force is the same. I have the weight force. I have what the weight of the car divided by 4, the weight of the car divided by 4, because it's 4 wheels. So that means here I have weight of the car divided by the blue area, and the blue area, of course, is bigger than the red area, right? So which one has the higher pressure?
The right one.
Exactly, right? You have a smaller area, same force, of course, your pressure goes up. So, so now what, right? Same. So in that regards, you have the same height of the wheel. So now, does the height have any impact here? No. Even if there's, but if I would have a smaller tire here, now that's the point now. So if I would have a smaller tire here, then of course the um, the area, and it's still a comparatively the same depth of the wheel. So of course you have a little bit of a lesser contact. So the weight, it goes even higher up because it even is a bit less. So the force here is even, or the pressure is even higher because the contact area is even less because the diameter of the tire has changed, hence the contact area has changed. But if you look from the outside, it has like less height, right? But the pressure is higher. Do you see what I mean?
Yeah.
So if I would argue now with the height of the tire, which would be a bit silly, but just to say, is the one which defines the pressure on the ground, then this one has a lower height, so it would have a lower pressure. No, of course not. Totally wrong, right? Because there's other effects in place. That's what I want to say. Here it's the surface contact area becomes less because it's force over area. And the force is defined by the mass of the car. And this is a bit going back to this one. It's the mass, like, or what you just sent me. It's the mass which is contained here. And of course, the area here is the same. So it distributes it all across X and Y. The pressure is the same here. Like in the example of the tire, the pressure from the same tire, oops, sorry, where do we have it? So it disappeared, excuse me, here. So the pressure of the tire is, this is the area, right, which is getting smaller and smaller, actually. But inside that area, the pressure is everywhere the same. So it doesn't matter if it's in the center of it or at the end of it, even if we have the axle here. And so here you may argue, well, this isn't there the highest force, and this is already a bit distributed. Yeah, in reality, yes. There's still a bit of higher pressure here because the force impact makes it as such that it fizzles out a bit. But that gets so complicated, so we simplify and say, nope, it's the same force. We assume it's in the center, but it distributes it over the area evenly. Hence, the pressure is the same all across. If you would make a micro measurement of the pressure, you would not get that total even pressure picture, actually. You would have different colors for different pressures, so to speak. So it would not all be blue here. It would be a bit more red, more dark blue, so to speak, to the center, and lighter blue to the outer part here, because the force distribution is really as such that it's a bit, well, distributed and not just all across the same. So that's why such an example is a bit tricky to deal with. That's the bottom line. To my opinion, you nailed it and say, well, it's actually the volume which is relevant for the mass, which is relevant for the force, and that drives it. So if I have that differently distributed, I will have the same pressure actually, because as like what you said, let me see here. I assume I have the same area. So, I mean, I can't really take it. But if you say the bottom area in both left and right body is the same, then of course I have the same pressure all across. It would be different if I would have a different area in the two bodies left and right. Hmm? Like with the tire, right? So how high the water column is on the left side compared to the right side is irrespective, because you have the same, like what you told me, the same mass of water in both bodies. Hence, you have the same weight force in both bodies. And assuming that the area at the bottom is the same in the left and the right body, you have exactly the same pressure. So that has not. So then it comes rather to the tire analogy in play, that you say, well, if the right area has a lower area, sorry, the right body has a smaller area, so it's not as wide as the other one, then of course the pressure changes. That means you change the dimension of the whole body from left to right, so to speak, so that the contact area is different. So the width and the length, or the width and the depth actually, is different. Then of course you have a different contact area, and then you have a different pressure. But as we said, we are assuming it's the same area, the same contact area. That is very important for what we say here. Then of course you can say left body has the same contact area as the right body. So in simplest terms, they have the same width, because the depth you assume anyway is the same. They have the same width. Then as long as they have the same mass, the height is completely irrespective. And that is a bit tricky for these water calculations. Because what counts is, right, you rightfully say, it's the mass, also meaning the body force, the weight force. And it's not just that you have on the one with the very height water column, you may say you have the, if you would of course stop at the height of the water column on the left side, Chris, if you take the long one, the high one, and if you, before you go into the square, there of course you have a very high pressure, of course, right? I mean, let me, we close soon, but this is what I want to say is, if we take your drawing like this, very high, and then we have this body, or we have the same body, but it's distributed like that. Hmm? And 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 of course now, and assuming now, well, that is not the best of examples, something like that. So we say this red part is the same as this red part, in terms of volume.
Yeah.
So volume, volume, and this one, same thing, volume, volume. They're identical. Then then that height is absolutely irrespective for the point here and the point here. You have exactly the same delta P, because you have the same volume, you have the same density, of course, water. So in the end, you have the same mass. Hence, as you have the same mass, is the same mass. Hence, you have the same weight, you have the same weight. Hence, you have the same pressure, regardless of the dimensioning of the whole thing. So the tricky part that with this height calculation, right, and say, well, just take the highest height and multiply it with everything. Nah, not really, actually, but I don't want to argue. Ultimately, I just want to say I like your argumentation line. This is ultimately the right way to go. Everything else is a simplification, which in the end is not necessarily leading to the right conclusion in real life. Like a bit with the resistance, air resistance, for example.
Yeah.
That's why. But of course, if I go to this point here, to this delta P and this delta P, so if now that area is the same as this area, then of course even that delta P2 and that delta P1 are the same because they have the same area, right? And they have the same volume, as we said. So the shape of the volume doesn't matter as long as they have the same, or the height, sorry, that height doesn't matter as long as the volume is the same. So, and we say the volume is the same. So, and then just have to have the same area. If the area is different, it's like with the tire, then of course the pressure is different. Why? Because of course then it's force over delta force over area. But as long as the area is the same and the volume is the same with the same material, so the force is the same, the area is the same, then of course I have the same pressure. I hope this helped.
Yeah.
Is that okay, Chris?
Yeah.
Okay. All right. Okay. So yeah, good. Um, then well, we just continue next time. Is that okay with what we planned for today? Go further with the electricity.
Yeah.
Okay. Have you done anything already in electricity, by the way?
We just started today.
Okay. Well, then it's good to have a couple of questions because I have a couple of questions from last time. Excuse me, over here, which we can go through. Other than that, we will start with Kirchhoff's law afterwards, which is for the circuits. That is a bit challenging then at some point. I think that electricity is okay. We can maybe do 20 minutes of that and then start with the Kirchhoff laws.
Okay.
All right. Okay. Thank you, Chris, and have a good week and see you next Friday. Yeah.
Yeah. See
Thanks. Bye.
you. Who the fuck is calling me? Orange question. My brain is taking these dies.